Hi, this is Patrick Shaughnessy. I'm going to be programming with audio. I've been working on this game program, showing the steps of that programming project in a series of videos. And I'm now at a point where I want the game to have sound effects. And to program the sound effects, I'm going to be using the JavaScript AudioContext. This is not the only way to do sounds in JavaScript. You can have audio elements in your HTML page and trigger them programmatically. But if you want to generate your audio at runtime, then you can use the audio context for that. Also, the audio context gives you the ability to spam an unlimited number of the same sound overlapping, while with audio elements, the element is either playing or not playing. You can't have one audio element in your page playing twice. What I'm going to do with the audio context is generate some simple waveforms and play them through it. Before I get to the actual programming, I want to talk about waveforms a little. And with that, I will switch to Audacity for a moment. So Audacity is a program that edits audio, not like LMS edits note events. LMS is a sequencer. Audacity is like the MS Paint of working with audio. You edit the individual samples of audio. I'm going to hit the generate here, generate a tone. Let's say I want a 300 hertz sine wave for a quarter second. So we have this sine wave. We have a time at the top, and if we zoom way in, we see individual audio samples. The lines between these dots just show abstractly the ramping between them that happens. The dots are the actual audio. And if I wanted to, I could actually manually edit them. You don't normally do this in Audacity. You edit things by applying effects to them. But the idea is that you're working directly with the audio samples, which is very different from something like LMS, where you're editing at a more abstract level. Now, the reason I'm showing you Audacity is just so I can show you a few things about the waveform graphically, because once again, it's a JavaScript, it's all going to be code and no graphics. So this sine wave sounds like that. If I go ahead and instead generate a 600 hertz sine wave instead of a 300, let's line those up so we can compare them easily. We see that at 600 hertz, we have twice as many waves per unit time. This is 300 waves per second. This is 600 waves per second. Oh, it's playing them simultaneously, right? That's just the 600. That's just the 300. So the higher pitch has more waves. And if we zoom in, we see those points are the same spacing apart. We didn't change the spacing. So we have fewer points defining each wave of the higher pitched sound. And we can, of course, show other types of thingies. Like I want to be at a new track when I do that. I'm not explaining the Audacity interface right now because the point is just to have something to show waves in. So a saw wave looks like this. The samples ramp up and then go back to 0 or to -1. And if we compare here, the rate is the same. This is 600 hertz, this is 600 hertz. They're both repeating at the same rate, but where this has a soft up and down wave, this is a very sharp slanty thing. Now, volume is, as one might expect, how big or small the wave is. If I use this amplify effect, turn down some decibels, then we see the wave is the same shape horizontally, but vertically it's been scaled down, and it's a softer sound. Not softer in character, just it's being played at a lower volume. And of course, volume, let me undo that, amplify. Volume can be so that changes over time too. Like there I use the fade in effect. So we see now, we start with these triangles going very small up and down. They end up going to full size later. And that's analogous, not even analogous, is how attack in LMS works. And fade out is likewise how decay and release in LMS works. So what we want to do in JavaScript to generate a wave, each of these dots is at some height. This center height is 0. The bottom and top are -1 and +1. And we just want to generate this curve, or this curve. We want to generate the curve that is whatever sound we want. That concludes the graphical explanation of how these audio things work. If necessary, I'll come back to Audacity. I'm not going to close it all the way. But from here on, I'm going to be dealing with code. So, the first thing we need is an audio context. All right, our ACTX. This is much like the canvas has a context, the audio picture has a context. But where the canvas context is bound to one canvas, and you could have more than one canvas on the page at a time, there's just one audio context. ACTX equals new audio context. All right, so I'm making a float32 array that's 48,000 things long. Now, the reason I'm using a float32 array instead of just a regular JavaScript array is because that's ultimately what I need the audio context to use. This is one of those APIs that's talking to hardware, much like the 3D accelerated graphics context, and it needs to be using typed arrays to do that efficiently. Now, for var I equals 0, I sound.length. Sound I equals, let's just do something. So a random number from 0 to 1 times 2 minus 1, so it's a random number from -1 to 1. So we're populating this sound array with completely random values. Now I'm creating an audio buffer. Oh, now I remember. You create the buffer first. That gives you, right, okay. Yeah, we don't need that var sound, actually. We're creating the buffer to hold the sound in. All right, so I'm creating a single channel audio buffer that's using 48,000 samples per second, and that is itself 48,000 samples long. One channel meaning it's going to be mono rather than stereo. Var buff equals that. Okay, now we get channel number 0 out of that, the only channel. And that gives us the array that we can then populate. And then we make a buffer source. So the audio buffer can be reused many times. Each time you use it, you make a new buffer source. This is analogous in some way to the buffer is like an audio file and the buffer source is like an actual audio element on the page, but it's not a close analogy. Source.connect ACTX.destination. So what this does is tell it when I am playing out of this source, the place I play out to is the ultimate destination of the audio context, as opposed to playing it to some filter, which is then playing to the destination more indirectly. Source.buffer, and when I play this source, I am playing this source by reading this audio buffer, which I created and populated. All right, and then source.start will play it. An audio buffer source will just play until it's done, and unless it was set to loop, they will then be done. Like the object will garbage collect as soon as possible. The buffer, however, will stay around if anything is using it, but as soon as that's done, the buffer is going to be gone too because I'm putting in a local variable here, not a global one. So every time I call this, I'm creating a completely new sound, 48,000 samples long. Maybe a little inefficient, but I'm not worried about that right now. All right, now I need to line up my thing. And I see I've got an error. Missing semicolon after for loop. Line 468. Oh, yeah, I just was getting my for loop syntax confused. This is the semicolon version. You need to explicitly increment. All right. Key fresh. That should be keys fresh. That's just a mistaken interaction with my other game code where the thing that was checking the keys was a certain name. Great. Now create audio buffer. Oh, yeah. Usually you leave out the word audio. Yeah, I think it's just create buffer. Oh, reload. Buff.data is undefined. Oh, you just, yeah, I was thinking something else. They had just buff.get channel data. What's going on here? Yeah, I never said that was var sound, right? I just have the word sound and no declaration. Okay. That last time I mashed the Z key a little. So I press Z, it plays this sound. Now that's kind of silly, but let's do this. Instead of just taking that, let's say times I over 48,000. So I'm applying a sliding modifier. Much like what I had in Audacity, that's an attack. Now let's make this, instead of a random number, something a little more interesting. Sine. Let's make it a sine wave. Sine. I times 2 times math.pi. Try to remember the exact trick here. Okay, there's a 48,000 samples per second. So 2 pi period is equal to 48,000 samples per second. Right. That would be 1 hertz, but I want it to be more hertz than that. So let's say I times 440 times 2 times math to the pi over 4800. Good. That worked. So I'll explain in more detail now I know it works. All right. So your sine wave it has a period of 2 pi. So it loops on itself every 2 pi. What we wanted was a sine that loops on itself every 1/440th of a second. But a second is 48,000 of these samples. And when we do all the math, we end up eventually, we multiply by the frequency, multiply by the 2 pi, divide by the samples per second. And that gives us the necessary chunk of math to make that sine wave for 40 hertz. Now, what I did that last time, you might have heard it, was I was mashing the key. And at that point, the browser was getting a lot of sounds overlapping each other and deciding on its own what to do because I wasn't telling it what to do.